everyone, welcome to the Chapter 4 Part 2 vodcast. This is a continuation of my previous vodcast on Chapter 4. We have a lot of topics to cover. We are going to look at acid-base theory, oxidation versus reduction, just kind of a simplified overall picture. It does get a little bit more complicated later on. And then finally we'll end with molarity dilutions and titrations. Alright, without further ado, let's begin. We'll start off with a very simplified theory that came from this gentleman, Svante Arrhenius. He said that acids were hydrogen-containing compounds, and when they ionize or dissolve in water, they will produce hydrogen ions. Now, this is kind of new for some of my students who I had last year. I just want to make sure that you know that a hydrogen ion sitting alone by itself is fairly highly reactive, and when it actually is in the presence of water, it will combine with water to make this guy. This is known as the hydronium ion. Instead of saying H2O, we sometimes say H3O, and because it is an ion, we put that little positive charge on there. Alright. Anyway, he also said that bases are compounds that ionize, and when they do, they produce hydroxide ions. Alright, so acids make hydrogens, hydroxides make OHs. So to give you a little bit further explanation, not all compounds that contain hydrogen are indeed acids, but also not all hydrogens in an acid are typically released as hydrogen ions. A lot of fatty acids, they will release just one of the hydrogens, and all the other hydrogens stay connected. So only the hydrogens in a very polar bond are ionizable or releasable. Remember, there are really strong acids, but there's also really weak acids too, which we need to discuss. So typically a strong acid like hydrochloric acid, when it's in the presence of water, it'll produce those hydrogen ions that connect to water, known as hydronium. So this guy right here is actually the hydronium ion because the water has combined with the hydrogen ion. And then the chloride separates, and so basically you have two separate ions, and that's what a strong acid will do. So what do we do about these acids that don't necessarily release all of their hydrogens? Or maybe what do we do with these acids that don't necessarily have a hydrogen in them? So the next theory came from these two gentlemen. This is the Bronsted-Lowry theory behind acids. And it says the next theory came on acids and bases from these two men around 1923. These guys define an acid a little bit differently. They define an acid as a hydrogen ion donor. Kind of makes sense, right? But they define a base as a hydrogen ion acceptor. Anything that takes on a hydrogen ion is considered a base. Fascinating. The reason why that's so fascinating is because for a long time, the scientific community actually did not have the correct formula for ammonia. Ammonia is a special case because you see the way that you make ammonia and the way that it behaves like a base is not evident from its formula. So right here, this is the formula of ammonia. It's NH3. And NH3 behaves basically as a base in water. So where's that OH? You know, if we were thinking about the Arrhenius definition of an acid or a base, you know, I don't see the OH sitting here. In fact, I see some H's in the formula. So you would think from Arrhenius that maybe that should behave as an acid, but it's the exact opposite. What actually happens is when ammonia is placed in water, it will produce these hydroxide ions, which will pick up on, you know, certain pH paper as a base. And then you'll have these leftover ammonium ions, okay? So the way that that happens is really kind of neat. This water is going to release a hydrogen and give it to ammonia. Now I want you to think about the Bronsted-Lowry definition of an acid and a base. Technically an acid is anything that releases a hydrogen ion, and a base is anything that can receive that hydrogen ion. So does that actually mean that water is behaving like an acid right here with ammonia? Well, according to the Bronsted-Lowry theory, yes. Water donated that H+ ion to ammonia, so therefore it's behaving like an acid. So take another look at that equation that we had for ammonia being dissolved in water. Did you notice the equilibrium sign? It was the arrow that points in both directions, because you really need to pay attention anytime you see that sign. That actually means that there is a reaction that is proceeding from left to right, from reactants to products, but there's also a reverse reaction going in the opposite direction. So look at that equation one more time. If we thought of it in the reverse direction, you would technically have these ammonium ions, the NH4 plus ions, reacting with the OH ion in the reverse direction to make your ammonia and your water. So if you thought about the reaction proceeding in the opposite direction, technically that means that one of these hydrogens from ammonia is being released, making him behave like an acid. And the OH ion actually received the hydrogen, making him behave like a base. So it's because of this Bronsted-Lowry definition of an acid and base that we come up with this new kind of theory of these things called conjugate acids and bases. Conjugates are just kind of like the related kind of stepbrother or stepsister to the acid or to the original base. So if you go back and you look at the original reaction, okay, you know that the starting ammonia was your base because he wanted to receive the hydrogen. But over here, this guy right here, now that he has the hydrogen ion attached, if you think about the reaction going in this direction, look at this guy. He is actually going to be donating the hydrogen, right? Well, we call him the conjugate acid to ammonia. Now look at water. We already established that water is behaving like an acid on the left. So on the right side, think about the reaction going this way. Technically, the OH received a hydrogen, making him behave kind of like a base, right? But we call him the conjugate base to water. So technically what this is this is the conjugate base to water, to H2O, and this guy right here is the conjugate acid to ammonia, NH3. So conjugate acids technically have one additional hydrogen, and conjugate bases have one less hydrogen. The only thing that I would add here to the conversation is just to make sure that you know that every acid has a conjugate base, and every base has a conjugate acid. There is one more theory that we should discuss, and it comes from this gentleman, Gilbert Lewis, a lot later on than some of the other theories. So he defined a substance, any substance, that can accept a pair of electrons to form a covalent bond as an acid. And then he also defined a base as a substance that can donate a pair of electrons to form a covalent bond. So in the first one, you have an acid that receives a pair of electrons, and then in base, they donate a pair of electrons, which is interesting because in some substances, we have certain acids and bases that don't necessarily have to have a hydrogen in order to form a acid or a base solution. So let's just take a look at this example here. This guy right here, the BF3, really peculiar little bugger, he can act as a Lewis acid. So check this guy out right here. Sometimes it's helpful to look at the Lewis dot structure, and if you've never seen a Lewis dot structure before, it just basically describes the number of valence electrons that are on the outside. Anytime you see a line, like over here, anytime you see a line, that means that what you have are two electrons that are being shared. In other words, a single covalent bond. These guys right here are electrons that are not in a bond, but they're around the outside of the atom. And if you'll remember with me, the stable configuration of the number of valence electrons around an atom is 8. Okay? So what you have over here is you have a the product here, BF4. All of the fluorines have a octet, 8 valence electrons, but the overall charge of this entire compound is a negative. It's a -1. But what's fascinating about BF4 is that when it's in water, it will actually have a tendency to pull the water a little bit in a separate direction, causing the overall acidity or basicity of the solution to change. Crazy stuff. Trust me, this is not covered very much in depth on the AP exam, but it is helpful to know because sometimes they ask you to discuss which theory best describes one particular acid, and they'll give you pictures and diagrams and stuff like that. So important to know, but not super important to concentrate really hard on. All right, moving on a little bit here. We're done with the acid theory. Let's look at some reactions that are double replacement reactions that don't necessarily produce the product anticipated. This is especially true anytime you have carbonates. So here's a good example. Calcium carbonate, I think that's limestone. When you react it with hydrochloric acid, the H in the front will combine with the CO3 to make what you would think would be H2CO3. You would expect to see that on the product side. But that is not the case. And by the way, you can't really see the arrow. I don't know why my PowerPoint arrows are not coming through, but there's your product. So we don't get this product. You will never see this product on the product side of any double replacement reaction on the AP exam. This guy will actually decompose because it's so unstable. This is carbonic acid. Carbonic acid is so unstable that it will naturally decompose into CO2 and H2O. Carbonic acid isn't the only one that will do this. Here's a couple other examples. So if you look here, we have sodium hydrogen carbonate in the second example down here. And don't let the hydrogen carbonate confuse you, because as you can see, it will do the same exact thing. All right, it'll take the hydrogen in the front of the acid. You would expect it to make H2CO3, but it doesn't. It actually will decompose into CO2 and H2O. So don't let hydrogen carbonates get in the way of you processing what the products are. It's the same thing. So carbonates do that, but so do sulfite ions. Sulfite ions, when they react with an acid, they will produce the traditional salt that you would normally expect, you know, the cation and the anion here and here. Sorry, this is where the arrow is going to the product side. So we have our typical ionic compound. You would expect the H and the SO3 to produce H2SO3, but that is not the case. You will never see H2SO3 as a product. This will naturally decompose into SO2 and H2O. There's one more nasty little product that you should be aware of anytime you see it. This is a nasty one. So anytime you have a sulfide ion reacting with an acid, okay, this product over here is actually a gas. H2S is not necessarily an aqueous product. We need to be on high alert anytime you predict this as a product, because I'll tell you from experience, this has happened twice in my lab when people didn't expect it to be produced and they were not underneath the hood. Oh my gosh, it smells so bad. This is like stink gas, basically. So just be very extra cautious about whenever this gas is being produced, you need to be underneath the hood. It smells like rotten eggs. All right, we're finally moving on to one of our last topics, which is oxidation reduction reactions. So I'm going to give you just kind of a brief overview of the difference between oxidation and reduction. Oxidation occurs when an atom loses an electron, and reduction occurs when an atom gains electrons. But here's the thing. In any kind of chemical reaction, you cannot have one without the other. Okay, if something's going to gain the electron just can't come from outer space. It has to come from some other substance that was in the reaction container. A great little way to remember the difference between oxidation and reduction is oil rig. Oxidation is loss, reduction is gain. Now another thing that you need to keep in mind, because this can sometimes get a little confusing, just remember, electrons are negative. So if you lose negative things, you will become more positive. And if you gain negatively charged things, you will become more negative. Try to remember that. Sometimes figuring out who is oxidized and who is reduced can be pretty tough. So what we actually have to learn about is how to assign oxidation numbers to an element in a compound, or maybe even an ion. And sometimes it gets a little tricky, but I've got some good tips for you. So make sure you copy this down. Here we go. Whenever you have an element in their elemental form, you automatically assign them an oxidation number of 0. And I gave you some examples. Remember, your diatomic gases, like oxygen, nitrogen, fluorine, chlorine, bromine, anyway, the list goes on and on, those diatomic molecules have an oxidation number of 0. So try to remember diatomic molecules have an oxidation number of 0. And then finally, metals in their singular form, in their natural state, those also have an oxidation number of 0. So bottom line, elements have an oxidation number of 0. That's one rule. Another really important rule is that the oxidation number of a monatomic ion, so any kind of ion, is the same as its charge. So if you were to see, for example, Mg 2+, guess what? Its oxidation number is 2+. And then if you saw a fluoride ion, F -1, its oxidation number would be -1. So if you have a monatomic ion with a charge, whatever its charge is, that is his oxidation number. Another rule to keep in mind is that nonmetals tend to be negative. Their oxidation numbers tend to be negative. And then metals tend to be positive. But we do have these rare occasions in which you might find yourself with a nonmetal, and the only nonmetal that I can think of that I've ever seen examples of is hydrogen. Sometimes hydrogen can actually have a positive one, but it's a negative one, which is very, very rare. Okay, oxygen typically has an oxidation number of -2. The only exception is when you have the peroxide ion. Okay, the peroxide ion actually has a -1. So if I gave you a bottle of hydrogen peroxide, each oxygen would have a -1 oxidation number. Hydrogen peroxide looks like this, H2O2, that's the formula. Each hydrogen would have a +1 oxidation number, but each oxygen here would have a -1 oxidation number. So if you had 2 positives and 2 negatives, the overall, charge of this compound would be 0. That's why it's stable. So every once in a while we have these weird exceptions, and I thought I'd show you an example. And if you see here, this came from chemguide.co.uk from the internet. And I just wanted to show you a few examples. I'll put this web link on our class website if you're interested in some more examples that are kind of peculiar. You're not going to see this very often, but it's good to know. We have these things called metal hydrides, not hydroxide. Hydroxide is OH. Metal hydride. Hydride is the H ion when it presents itself in the negative form. Very, very unique. So I will post some of these examples. I've already talked about peroxide. You see that right there. But anyway, I'll put these on the websites. These are the weird ones. You're not usually going to see it, but I thought I'd mention it, okay? It's good for me to just I'd rather cover all my bases here. A couple other rules is that the halogens are right next to the noble gases. It's a family right next to them. They are always, always, always -1. You want to know why? Because they have really powerful electronegativity values. So anytime you see a halogen that includes fluorine, that whole family right there, they will be a -1. Okay? Always. All right, so a couple other rules you want to keep in mind is that nonmetals tend to have negative oxidation numbers, but you can have a couple incidences where they might actually be positive. Now, if you have a periodic table, look at the family that's right next to your noble gases. Those are called your halogens. So the most powerful halogen there is fluorine. Now, I want to make sure you know that fluorine will always, always, always have an oxidation number of -1. But some of those other halogens, they can actually sometimes have a positive oxidation number. It's not very common. So I did want to explain what an oxyanion is. Now, in your textbook, you can flip over to page 61. But basically, an oxyanion is like your chlorites, your chlorates, like hypochlorite, carbonate, nitrate, phosphate, sulfate, perchlorate. You hear the eights and the ites, right? Those are your ions. You know, they have negative charge that are considered oxyanions. So for whenever you have an oxyanion, you need to assign your oxygen with the -2 charge. Okay, the oxygen will have the -2. And then the halogen or the other nonmetal attached to your oxyanion, so the polyatomic ion, these are the ones that could potentially actually be a positive charge. So before I jump into a few examples on how to do these, I do want to make sure that you have a couple other rules. So the sum of the oxidation number for all the atoms in a neutral compound, so when you add them all up, in a neutral compound, say like NaCl, they have to balance out to be 0. So if you think about salt, NaCl, you know that the Na has a positive charge, +1, and the chloride has a -1. The oxidation number in that compound of sodium would be a +1, and chlorine would be a -1, and they balance out to 0. So ionic compounds, or compounds that have a neutral charge, you know, we'll look at a few of those to see how well you do for examples, okay? Just give me 1 minute. The other thing that you also need to be aware of is that if you have a polyatomic ion, all right, polyatomic ions have charge, right? So the overall sum of all the oxidation numbers of the atoms that make up a polyatomic ion, it has to equal the charge of the polyatomic ion. All right, now let's dive into some examples. Let's find the oxidation number for each of the elements in sodium sulfate. All right, step 1, is the substance an element? No, it's a compound. Step 2, is the substance ionic? Yeah, it is actually. So this is an ionic compound, and therefore all of the oxidation numbers of all the elements inside of there need to have an overall charge when you add them up to be 0. Step 3, if the substance is ionic, are there any monatomic ions present? Yeah, there's one monatomic ion, and that's sodium. Sulfate is polyatomic, and so we'll have to rip that guy apart a little bit to get, get the other oxidation numbers. All right, so right now we know that sodium has an oxidation number of +1. Now, you'll notice that we had to use 2 sodiums in the compound. So technically, on the positive end of the ionic compound, you have 2 +1s. That gives us an overall +2. What that means is that this sulfate, which I'm sure you already know, the sulfate ion has to have an overall oxidation value when you add up the sulfur and the oxygen of -2. So are there any elements in sulfate that have specific rules? The only one that we have for sulfate is the oxygen. So anytime you see oxygen being used, you can pretty much assume that it's going to be a -2, unless if you look at the name of the compound, it says peroxide. Okay, so sulfate is SO4. It has an overall charge of -2 charge. So oxygen has a -2 charge each, and you will notice that we used 4 of them, correct? All right, so oxygen is pulling right now, all 4 of these oxygen is pulling a -8. All right, so this oxygen right here, the oxygen chunk of 4 oxygens is overall a -8. So remember, we want to make sure that when we consider the oxidation number of sulfur, that we are going to make sure that no matter what, the leftover balance is -2. So what -8 will still give us a -2 charge because sulfate is -2. So do you see how you have to figure out X? You have to figure out sulfur. See, we knew what sodium was. We knew that oxygen had a rule, so we just had to figure out the leftover sulfur. So you're just basically solving for an unknown. So we have sulfur that we need to just figure out, and I think you guys saw in the previous slide, basically sulfur is going to have, right here, is going to have a +6 charge. All right, so oxidation number of +6 on the sulfur. So let's try another one, maybe one a little bit harder. So this is K2C2O4. Let's check this one out. So is the substance an element? No. Is the substance ionic? Yes. All right, are there any guys in here that we might be able to, have a rule for? So if you look at the guy in the front, this is potassium, and potassium, you have two of those potassiums sitting in there. So potassium is always going to have a +1 charge. He's monatomic. And I want you to notice that you actually did use two of the potassiums. So technically we have an overall of a +2. So whatever else is left on the compound, this guy right here, the C2O4, this C2O4, since this is an ionic compound, it must have an overall charge of -2. All right, in that C2O4 that we know has to have a -2 charge, are there any elements that have specific rules? Yes, your oxygen does. So oxygen has to be able to pull a -2 charge. You'll notice that in this guy, you have 4 oxygens in there. So if oxygen has to be -2 each, and you have 4 of them in there, these oxygens right here are pulling an overall -8 charge. So the only one that's left that we have to figure out is carbon. So the overall ion has to have a -2. So something minus the 8 on the oxygen has to give you an overall balance of -2. What is your X? Because that's your carbon. But here's the problem. You see how you don't have just one carbon? You actually have 2 carbons. So to make this work, you have to remember that you have 2 of those carbons out there. So you see how the algebra changed just a little bit? So if you look at the way that we solved this, you'll notice that we had to have 2 carbons in our little algebraic expression. Therefore, the charge of each carbon must be a +3. The oxidation number for carbon is 3. Oxidation number of oxygen was -2, and the oxidation number of your sodium in the front was +1 each. So when we use oxidation numbers, sometimes it's helpful to look at single replacement and double replacement reactions to identify which element was being oxidized and which one was being reduced. So in this particular example, what we have is we have a container, a little beaker, that has some hydrochloric acid in there, and they stuck a magnesium zinc ribbon into it. All right, so in the process, I want you to look over here. It says, in displacement reaction, ions oxidize an element. The ions then are reduced. So remember, think about oil rig. Oxidation is when you lose an electron. So if you can zoom in real quick to page 139 of your textbook, or if you can see this picture really well, this is the image that is appearing on page 139 of your textbook. So look really close at what you see the elemental zinc doing. All right, if you zoom in right here. So zinc, a metal, and all metals do this, they have a tendency to like to release their electrons. Some do it more than others, and if they do it really well, they're highly reactive. So the zinc element is actually, if you look at the arrow, he is taking an electron away from himself and giving it away. So when he gives that electron away, the acid produces these hydrogen ions right here. And so if the metal, this metal right here, is technically losing electrons, I want you to think about what that is. That is oxidation. So the metal is being oxidized. Now, if the hydrogen ion is the one that's receiving those electrons, well then he must be reduced. And if he is reduced, think about what H plus aqueous, okay, if he gains an electron, that would make this plus sign go away. Now, hydrogen doesn't like to just be by himself. In fact, in Mother Nature, we don't like to see hydrogen ever by himself. He just won't do that. So what he'll have a tendency to do is find another hydrogen that was also reduced at the same time. And when these two find each other, you see all these bubbles right here? They form hydrogen gas. Here's another example. So this is another single replacement reaction, and this image does appear in your textbook on page 141. So in this reaction, the silver ions, now the ions are in solution, they oxidize the copper metal. So this is a little bit different, isn't it? So I want you to think about what's going on with the copper. What does the copper have to do in order to get into solution? So copper has a positive 2 charge as an ion, okay? And if you look back over here at the very end, you'll see that you have a positive 2. That is a copper ion that has been ripped away from the metal and now has a positive 2. So he went from being neutral to having a positive 2 charge at the end. Think about what that would mean. Remember, electrons are negative. So if a metal becomes positive, the only way that you become positive is if you lose your negativity. Copper lost electrons. So this metal literally gave 2 electrons away. Each one of those copper elements gave 2 electrons away into the solution. Now you're probably asking, who received those electrons? And that's a very good question. So in solution at the very start, you have these +1 ions. You know who that belongs to? Silver. So every time one of these coppers gives away 2 electrons, those 2 electrons are going to find 2 silver ions in solution. Because remember, electrons are negative, they're going to be attracted to positive material. So they will find those cations that are in solution. And lo and behold, you will literally make solid, pure silver. You see the color changed over here? So these ions actually solidify, and that's what you're seeing right here is pure silver solidifying on the outside of that copper metal. Isn't that super cool? So copper lost electrons, silver gained those electrons. Copper technically was oxidized, silver was technically reduced. Here's an interesting question for you. Would we be able to reverse this reaction? In other words, could we make that silver go back into solution? You know, you got solid silver being produced. Could we actually produce and get back the silver ions and, you know, we could change back that blue copper solution? Can we change it back to get just the copper? The answer is no. The reverse reaction does not occur, which should make you ask, why not? The reason comes from what we like to call the activity series. So we have an activity series for all substances that we know of that are metallic, metal. Now remember how I told you that sometimes hydrogen can behave like a metal, especially in acids. So you'll notice a very special location on the metal reactivity specifically designated for your hydrogen. So anything that is above hydrogen, you know, higher in reactivity than hydrogen, will actually react with acids. Anything that is below that hydrogen will not react with an acid. You see, not all single replacement reactions will work. So in the following examples, these reactions will not work. So the element that is single or alone needs to be higher in reactivity in order to push the reaction through. So in this first example, we would want to see the single element zinc to be higher in reactivity than magnesium. But if you look back, zinc is not higher in reactivity than magnesium. Zinc is located here. Magnesium, careful, it's not manganese, magnesium is much higher. So we would, if you want the reaction to work, you need the lone element to be higher in reactivity. In the second example, you would need silver to be more reactive than nickel. And silver happens to be a pretty stable metal. We like to wear it in our jewelry. We don't necessarily wear a whole lot of nickel. All right, so this would also be a no reaction. It would not work. And now finally, we're on our last little bit of information that we need to cover. Concentration. So concentration is a measurement of how much solute is in the solvent. The most common form of concentration unit that we use is something called molarity. Molarity is the number of moles of solute per liter of solution, and it's given the symbol of a capital M. So I want you to take a look at the picture on page 144 of your textbook. It is the procedure on how to prepare a solution of copper sulfate. So I want to ask, what do you think would happen if you filled up that glass flask all the way up to the mark with water first, and then you added 1 mole of copper sulfate to that? What would happen to the overall volume? Well, just like when you sink yourself down into a bathtub that is full of water, the volume is going to rise. And so you will have more solvent present than you actually needed to have because it's going to go over the mark. And it'll actually be less, ever so slightly less than a 1 molar solution. So the technique here is very important. You will be preparing solutions eventually down the road in lab. So let's get a little practice. What is the molarity of a solution made by dissolving 5 grams of glucose in water to make exactly 100 milliliters of solution? So the strategy is that you were given mass of your glucose. My first strategy is that I need to remember molarity is moles of solute per liter of solution. So I would have to definitely change the 5.00 grams into moles. All right, so this is C6H12O6, and we need to convert that into moles. So take a pause the video. Let's see if you can remember how to do a mole conversion. And then you were given actually milliliters of solution. So think about what you're going to have to do there to change the milliliters to liters. So to save myself a little time, at the very end of this problem, I know I have to take the moles and divide it by liters in order to change it to molarity. So what I did at the very end, I just want to show you. I knew that I had to divide by volume, and instead of wasting time on getting the answer of the moles first and then dividing by the liters second or trying to show my work, I just throw it right here just to save a little time. So I converted my mass into moles, okay? And then I divided the volume by liters. So you just need to remember how many times you need to move the decimal point over when you have milliliters and you're trying to go to liters. You need to move it 3 times. Okay, so I did all of that out, and let's get the answer. I get about 0.2775, and this mass right here has 3 sig figs. I probably should have put a decimal point right here because we're assuming that we're going to probably make this solution in a 100 milliliter volumetric flask. So I would assume that this would be 3 sig figs that we need in our final answer. So 1, 2, 3, you're going to want to round that 7 to an 8, and that would be molar. There you go, so 0.278 molar. So now that you know the technique of molarity, you need to also be kind of cautious that now we can actually talk about the concentration of ions in solution. So here is another example. What is the molarity of each of the ions present in a 0.015 molar solution of calcium chloride? Now, calcium chloride, the compound, has 1 calcium and 2 chloride ions. So if I was looking for the concentration of my calcium ion, all right, that would just be the concentration of the solution, because for every calcium chloride, I have 1 calcium ion. So this guy's concentration would just be 0.015 molar. But what would be the concentration of my chloride ion? You see, each of the calcium chloride compounds actually has 2 chloride ions. So I would actually want to double the concentration to be 0.030 molar, because every compound produces 2 of those ions. So molarity can now be considered a conversion factor, because molarity is a ratio between the moles of the solute and the liters of solution. And anytime you have a ratio, you can use that as a conversion factor. So don't forget that molarity involves moles and mass, technically. If I have mass, I can get moles, and that would be an easy conversion too, right? So take a look at this example. How many grams of sodium chloride are in a 250 milliliter solution with a concentration of 2.01 molarity? Since the question is asking us for grams, I would expect to be ending here at the very end. So molarity, I just explained, is a conversion factor. You would never want to start a problem with a conversion factor like molarity. So you know what I'm actually going to start with? This is where I need to end. This is a conversion factor, right? I'm going to start with the original volume that they provided in the problem. And I don't like to use milliliters, so I'm going to automatically convert that right here into liters. So this is the liters of solution that I have. The concentration of the solution is 2.01 molar. What that means is that each liter that I have of the solution would contain 2.01 moles of the solute. And what is the solute? Sodium chloride, NaCl. Now I need to end with grams, so I'm going to do one more step. You'll notice that the volume is gone. What is the molar mass of 1 mole of NaCl? Because that's how you're going to end the problem. So when I'm looking at all the sig figs that were provided to me, you know, I kind of wish that there was a decimal point right here so that we can call that 3 sig figs. I would anticipate 3 in my answer. So I would round this to say 29.4, and that would be grams. Final answer. So now that we're on the topic of molarity and concentration, let's talk a little bit about dilutions. Dilutions is when you basically water down a solution. So if you think about a really concentrated solution, if you add some additional solvent or water to that solution, did the number of particles of solute change? You know, we didn't add any solute, we only added solvent. So the overall volume of the solution changed, but the amount of solute in it, grand total, didn't change. Think about the law of conservation of mass here. So when we look at the number of atoms of solute remaining the same, you can actually do a really nifty little formula to help you with dilutions. So the unit for molarity is moles per liter. That's what molarity is. Now, the unit for volume, obviously, we like to use liters. So if you look at that, doesn't liters and liters cancel? Yeah? So in a dilution, the number of moles of solute is going to change. It's just the volume, or I'm sorry, the number of moles of solute is going to remain the same. It's just the volume that changes. There's a small technique that is mentioned on page 148 of your textbook. The technique that you're looking at is in figure 4.18. This technique is when you remove a very specific volume of a concentrated solution, and then you pour that very specific volume into another flask and then dilute it. It's called an aliquot. Okay, so here's an example. How many milliliters of a 3.5 molar solution of hydrochloric acid are needed to make 500 milliliters of a 0.10 molar solution? You can simply just use the formula for dilution to figure this out. It shouldn't be too hard. That is a question on your guided notes. Make sure you do it. Finally, we're on to our last topic dealing with molarity, and that would be the topic of titrations. Titrations are used to determine the concentration of an unknown solution. So in order to do that, you have to prepare a solution that you absolutely know the standard concentration of. This is called your standard titrant, or the stuff that is going to be poured in. So when you add an indicator to the unknown solution that will change colors at a very specific point, when you have the reaction completed, you will reach something called the equivalence point. So if you could look on page 150 and 151, you will see an example of a titration. So here's something that you need to also be aware of. You need to make sure that you choose the proper indicator. We want the indicator to change colors at just the right spot. And there's thousands of different types of indicators that change colors at different pHs. The basic titration setup is you keep your unknown in a flask. You put your standard in a piece of equipment called a burette. So this is your standard, this is your unknown. You will have a very specific volume of the unknown, but you won't know its concentration. So a standard titration problem has to give you the known concentration of the solution inside the burette, the titrant. You have to have how much of the known solution it took to reach your equivalence point, so how much was drained out of the burette. And you also have to know the specific volume or mass of the unknown solution inside of your flask. Okay, so let's look at an example. How many grams of calcium hydroxide are needed to neutralize 25 milliliters of a 0.100 molar HNO3, that's nitric acid. Step 1, this is the most important piece of your titration problem. You can't solve anything without first analyzing the balanced equation. So I lost my little yield sign here. Here you go. So it looks like nitric acid and calcium hydroxide do not have a 1-to-1 ratio. Do you see how it's a 2-to-1 ratio? All right, it's going to take 1 mole of calcium hydroxide, the base, to neutralize 2 moles of your acid. So these ratios are really important when solving a titration problem. Analyze all the information that they gave you. They said that 25.0 milliliters of 0.100 molar of the acid was used. They gave you the molarity and the volume. Guess what you can get? How many moles of acid was used. Now that you have the moles of acid, you can look at the balanced reaction to figure out what the mole-to-mole ratio is between the acid and the base. Don't forget to look back at your balanced reaction. Now, once you get your mole-mole ratio figured out between the reactants, you can do one last step. Convert that mole of the base now into the mass, and then you're done. Look at the work here that I did. So first, I took the volume of the solution that they originally gave us. All right, the volume of the stuff that we know the most about, okay, the standard. I always start with the volume of the standard, and I can't use milliliters, so I just cross-canceled my milliliters so that I could get to liters. Then after I got the volume, I converted the volume into moles. This is the molarity of the acid. This right here is the mole ratio from the balanced reaction, and then this right here at the end is the molar mass of my calcium hydroxide. So if you look very carefully, I very carefully cross-canceled everything I needed to so that I could end on mass. Titrations take practice, practice, practice. Make sure that you look over some of the sample problems at the end of this chapter on specifically page 152. All right, the book does a really good job at reviewing these concepts. I'll make sure that I post some additional information on your website to help you out with maybe some of the more difficult titration problems that you might encounter. But guys, all you're doing here is stoichiometry. That's it. You're looking at balanced reactions, you're plugging in information, getting to the heart of stoichiometry, which is that mole-mole ratio. I will be posting some additional support for those of you who want it. Some additional practice with molarity, additional information on gas-producing reactions, and additional information on titrations. And then I also want to throw in some of those weird oxidation number examples onto the website as well. I hope this information has helped you. We're done with chapter 4. Peace out.